Hello, this is the Majority on Bowie YouTube channel, where I post a new interview every week that always has something to do with David Bowie. And for daily content, visit the blog www.majorionbowie.com with new content every single day that almost always has something to do with David Bowie. Today, I am incredibly honored to be joined by one of the most famous and recognized physicists in the world, Professor Lawrence Krauss, known internationally for his best-selling books, influential public lectures, and frequent appearances on all forms of media, including alongside his friend Professor Richard Dawkins in the 2013 documentary film The Unbelievers. He was even nominated for a Grammy, though for writing not liner notes for a CD of music from Star Trek and not for doing a Bowie cover. Professor Krauss is president of the Origins Project Foundation and host of the Origins podcast, which I will link to in the show description. So, why have I invited one of the most famous scientists in the known universe to my Bowie show? Up front, I will say I don't expect to be talking much about David Bowie himself in this episode, though at the end I will ask Professor Krauss for his favorite Bowie song. But there is a remarkable overlap between Professor Krauss's subject matter and that of David Bowie. And there's one topic in particular that I think is particularly relevant. David Bowie recorded songs about stars, stardust, time, space, planets, faith and doubt, all of which Professor Krauss writes and lectures about, as well as, to the point of this discussion, nothing. Nothing is one of the most ubiquitous words in Bowie's lyrics, more than space, more than stars, and certainly more than love. This is a topic that comes up again and again on this show and in my blog in discussions with philosophers, novelists, musicians, and others. I have to admit that I fell down the rabbit hole of listening to Professor Krauss's lectures that are available on this topic, including a lecture on the origins of the universe that, as of this morning, has attracted more than 2.5 million viewers, a number that will surely be surpassed by this very episode. I should say that Professor Krauss has done much more. He did much more before, and he's done much more since publishing his 2012 best-selling book, A Universe from Nothing, which is an excellent book, which also does a great job of explaining, complicated matters for a general audience. And his most recent book is a book he's edited called The War on Science, which is about current threats to open inquiry and the scientific process. But today we're going to go back in time, as it were, and talk about nothing. So, Professor Krauss, thank you so much for joining me today.
Well, it's wonderful to talk about nothing.
So let me,
Anyway,
let me ask right off the bat, what is nothing?
that's not such an easy question, or it's an easy question to ask. It's not such an easy question to answer because you really have to think about it. Fundamentally, the way to think about nothing, in my opinion, the only appropriate way to think about nothing um, is to think about it from a physics perspective, and then it's quite clearly the absence of something, right? And then you have to be a little more productive and say, well, a little parse that a little more carefully. Um, what something is it the absence of? So, so first of all, it's a physical quantity in the sense that it's the absence of physical quantity. It's the absence of something. But the simplest thing to do, and I did that in my book, is say, well, the simplest version of nothing is just empty space, right? That's the nothing of the Bible. Vast, empty, void. And then, of course, physics has taught us using quantum mechanics and relativity that empty space is not so empty. It's a bubbling, boiling brew of virtual particles that are popping in and out of existence all the time. And then not only that, but those particles affect the properties of everything we see. The virtual particles they exist for such a short time you can't see them directly. So you might say it's like counting angels on the head of a pin, but it's not because um, they while you can't see them directly, like the Cheshire cat, they leave a little bit of an afterglow. They affect the properties of everything. All the particles we see, all the mass in your body, basically comes from almost all the mass comes from particles popping in and out of existence. Anyway, so that kind of nothing is quite interesting. It's because it's full of interesting stuff. The So empty space is the first version, but you might say, well, that's not really nothing because there's still space there. So the next version is no space and no time, because space and time go together. So no space, no time, basically no universe. And that's really the most interesting kind of nothing, okay? Because the question is, where did the universe we live in come from? And in what, and what is the universe we live in? It's a space and time. And could it be that neither of those things existed at some point? So I would say that's the most interesting kind of nothing, is no space, no time. But you can go a further step further. You can say, well, okay, no space, no time, but there are laws that are governing the universe. What if those laws didn't exist? And then that's sort of absolute chaotic nothing. And anyway, and so I step through each of them when I talk about
Yeah.
how it's possible that our universe came from nothing, in a universe of nothing. Um, and the most interesting version of that is that simply we have very plausible arguments for how our space, our time did not exist, and that did exist and come into existence just by laws of physics. And if you asked yourself, what would a universe that came into existence from nothing just by the laws of physics look like after 14 million years, it would look exactly the same as our universe. That doesn't prove it's the case, but it's highly suggestive.
Yeah. So you explain this in detail, but it's very a digestible detail in your book from
Yeah.
2012. Nonetheless, you got considerable pushback, especially and including from theistic apologists. And what's their pushback and what's your response?
Well, it's always hard to recreate arguments that one finds ridiculous. But but well, the simplest thing is a syllogism that William Lane Craig, like, a meaningless syllogism, which is that let's see, let me just see, something like all things that exist had a cause. The universe exists, therefore the universe had a cause. Basically, is the argument. And it's it's not true. First, even the first aspect of the syllogism isn't true. When I turn on there's proximate cause and then sort of vague causes. When I turn on my light here, I'll turn on this light. Maybe you'll see it. It's a daytime. You probably can't see
Yeah.
it. Okay, what happened? Well, atoms emit radiation when they're excited, and the electrons pop into energy levels, and then they relax. And we know that they'll relax, but each atom that relaxes, when it's going to relax, is just totally random, given the laws of, I mean, probabilistic, not random. Probabilistic. There's a probability that the atom will relax at a certain time, but you can't say which atom will relax when, because that's quantum mechanics. So there's nothing that specifically that causes each atom to relax. It just does. And the light, the photons that come out of that light didn't exist, by the way, before they were produced. They weren't hovering around in the light bulb there, or they were waiting for the atom to be excited and released. So when light is emitted from an atom, the light didn't exist beforehand in that atom. It was emitted in the process of that thing decaying, and that process of creating that light doesn't have an immediate cause. Okay,
Yeah. So
and
that
so
seems
so
related.
so our universe, if the origin of our universe is similarly quantum mechanical, then it can spontaneously pop into existence without any immediate proximate cause.
But when you say the universe pops into existence spontaneously, you don't mean the universe that we live in today. You're talking about,
Well,
uh,
the universe as it began,
yeah,
the Big Bang, the universe at the beginning of time that evolved after 14 billion years into into
yeah.
our universe. Although there's some arguments that suggest if the universe if space is infinite and time is infinite, that even universes that are fully developed, in which you and I are about to have this conversation, can pop into existence, and we would all have the memories of a universe that existed before, we all only existed for a few seconds. Highly unlikely, but anyway.
Well, that I was going to ask you this a little bit later. I was going to build up to this, but let me ask you now because you bring that up. I mentioned that you did liner notes for an album of Star Trek music. I didn't mention that you wrote a book called The Physics of Star Trek. which I
Mm.
read when it came out before I was paying
You're pretty
attention to who
young.
wrote it.
Anyway, yeah, no, it came out in what was it? Probably 93. Yeah.
Yeah, and like only when preparing for this talk with you did I make the connection that you were the guy that wrote that book.
Oh,
But
okay. Oh. Well, it obviously had a big indirect effect on your life. You just didn't know who
I
did.
just didn't know. But here's
Yeah.
my question. We're talking about Star Trek. Does Star Trek um, stimulate an interest in science? And regardless of the answer to that, you just described something that sounds like the multiverse, which is a
Yeah.
topic for scientific inquiry. It's also a topic for Marvel movies. But
Well,
does that advance scientific curiosity, or does it sort of stunt it because it gives the wrong idea?
well, I think it's hard. It depends who you are, of course.
Yeah,
I mean, science fiction. I think Stephen Hawking, who wrote the foreword for my book, The Physics of Star Trek, um, said science fiction, like science, spurs the human imagination, or something like that. So I think science fiction is fun because it gets people to ask questions, but it always is much less interesting than the science.
yeah,
Always. And often gets the science wrong. The important, when I first after I wrote the physics of Star Trek, I did a lot of TV shows with well-known science fiction writers, and one of the more well-known ones, whose name I won't mention, who'd written some of the early episodes of the original Star Trek, said that the operative word in science fiction is fiction. Science is just there to help move the plot along, but what's really important is a good story.
yeah,
So, and so there's no necessity to get the science right. As long as they don't make it so embarrassingly bad that you can't suspend disbelief. So the science fiction movies I find ridiculous are the ones I can't enjoy. The ones that are just something is so glaringly stupid that I can't, like Interstellar, that I can't suspend disbelief. Um,
yeah,
but I do think it does probably for some young scientifically inclined people. I used to say boys, but I don't think it's all boys. Um, I think science fiction had does serve a purpose when they're young of getting them interested in the possibilities of the real universe. They
yeah,
don't grow out of it, they may not grow out of it, but then they turn to science. But science fiction doesn't very rarely anticipates what's actually going to happen. Usually it misses the most important stuff.
yeah,
And then, the multiverse, Marvel, that's so that's even worse when they just pick up buzzwords and they just because the multiverse in physics are universes, if they exist, that never interact with each other in any way, shape, or form, and of course they're different than the multi. Even Star Trek had multiverses in a way, but it's very different. And so, yeah, okay, but I don't care. I mean, if it helps the plot, I don't mind so much. But yeah.
yeah. So let's go back to something more scientific, something that you touched on a few minutes ago. In describing nothing, the first iteration of nothing that you were describing in empty space, you said empty space is it's boiling with particles that are popping in and out of existence. Are those virtual particles? And if so, what are virtual particles?
Well, virtual particles are just this are examples like of every real particle can be a virtual. I mean, not itself, but electrons can be virtual or real. Quarks can be virtual or real. And what happens is that a real particle is something you measure. It's right there, electron. You see it. Okay, but the laws of physics, when you combine quantum mechanics and relativity, say that electrons can pop into existence. Electron-positron pairs can pop out of empty space, exist for a little time, and then disappear because because of the Heisenberg uncertainty principle. It basically says Heisenberg uncertainty principle says if I can measure a system for only a certain amount of time, then there's an uncertainty in its energy. I never know the energy of a system exactly if I can only measure it over a finite time. There's always some finite uncertainty. And if you don't know the energy of the system, well, quantum mechanics is basically, as I often say, is like the White House or corporate America. If you can't see it, anything goes. And so if the system can have a range of energies, then quantum mechanics and relativity basically say, okay, well, you can throw extra particles in there and they have more energy. Okay, but as long as they disappear in a time scale so short shorter than the time it takes you to measure them, then you don't violate any laws of physics. So if you can't measure the energy, then energy doesn't have to be conserved, right? Be, Energy is conserved in a system. But if I can't measure it, quantum mechanics says, well, okay, it's like catch 22. If you can't measure it, I can throw all sorts of other stuff into empty space that would violate conservation of energy, but then they'll disappear and time scale so short you can't measure it, and it's allowed by the Heisenberg uncertainty principle. So um, basically, that says that quantum mechanics says that empty space can have these particles that pop into existence. Any particle that exists in nature could pop into existence and then pop out of existence. But if it's very heavy, it's got a very big mass, it can't live for a very long time because you'd notice that violation of energy conservation much more quickly.
Yeah.
So virtual particles with heavy mass can exist from only much shorter times than virtual particles with light mass. And virtual particles with zero mass, like photons, can exist for arbitrarily long times because you can emit an almost zero energy photon. And basically, one way of understanding the force between charged particles is that they're emitting virtual photons that are being absorbed by other particles that are then being repelled. So, and bottom line is that every elementary particle that exists in nature can exist in the virtual form, but the amount of time it can exist for is inversely related to its mass. Okay?
So, nonetheless, this is happening so frequently that empty space has weight. Right.
Well, we'll get to there.
Okay.
It's happening so frequently that it affects the properties of atoms. In a way, this is how we know the virtual particles exist, because quantum mechanics allows us to calculate the energy spectrum of, say, hydrogen. And we get the answer wrong if we just use a proton and electron. Get the answer wrong by a small amount, part in a billion. But if we assume that electron-positron pairs could pop into existence for a little while, and the electron can hang around near the proton, and the positron can hang around near the electron because of electric charges, we can calculate how they'll affect the spectrum of hydrogen. And they change the spectrum of hydrogen so it agrees exactly to 13 decimal places with what we observe. It's the best measured prediction in all of physics. So we know virtual particles exist. And we can't see them directly, but we can measure their effects indirectly. Now, since the virtual particles in a proton, virtual gluons, they're called, pop into out of existence, we can calculate on computers, not first principles, but on computers, how much they contribute to the mass of the proton. And those virtual particles contribute most to the mass of the proton. In high school, you might learn that a proton is made of 3 quarks, but up and down. But the mass of those quarks is less than less than 1% actually of the mass of the proton. The proton gets its mass from all of the virtual fields, so-called gluon fields that pop in and out of existence. So bottom line is you might think, okay, well, if these virtual particles can give mass to protons, maybe they can give weight to empty space. And that's a good idea. And so we do the calculation and we find out the only ways we can do the calculation give us an answer that says the mass of empty space should be roughly 120 orders of magnitude greater than the mass of the observed universe. And that's clearly the worst prediction in all of physics. Um, so that's the situation that we theorists lived with in the 1980s. And the answer was, well, maybe there's some mathematical symmetry of nature we don't understand that cancels the positive energy contributions from some particles and the negative energy contribution from other virtual particles, and they cancel exactly and produce zero. Because after all, what's the only sensible value for the energy of empty space? It's zero, right? But we calculate it to be 120 orders of magnitude larger than the energy of the observed universe. There's no way we can cancel that and leave a very small number. We don't know how to do that. But we can cancel things exactly with mathematical symmetries, producing zero. So all of us went to sleep at night saying, okay, the energy of empty space is zero, and some new mathematical symmetry in nature exists that we haven't discovered, and that will help us solve all our problems. That was the conventional wisdom up to at least 1995. And then in 1995, we wrote a paper, and some other groups intimated as well, that maybe empty space had energy because there were properties of our universe that couldn't be explained otherwise. And one of the consequences of empty space having energy is that the expansion of the universe would not slow down over time, but speed up. Because if the weird thing about general relativity is if you put energy in empty space, it's gravitationally repulsive, not attractive. And energy in every other form is attractive. So if you fill up space with energy, it should cause the expansion of the universe to speed up instead of slowing down, as a sensible universe should do. And then in 1998 and 99, two groups discovered the universe was speeding up, not slowing down, much to their surprise. Even though one of them, I know at least one of those groups was doing their work to prove me wrong, to prove us wrong when we said the universe should speed up. And they discovered it did speed up, and moreover, it sped up by exactly the amount that more or less we predicted. But it was shocking that the universe is accelerating instead of decelerating. But that suggests that indeed the dominant energy of the universe does reside in empty space, and it was such a significant development that in, I guess, 2011, the Nobel Prize was given for that discovery.
Yeah. You wrote that paper you mentioned that you co-authored from 1995. You kind of didn't believe it yourself. You put it out there to
Of
see what the
course, well, yeah, I
reaction
put it
was.
out to be heretical because I
Yeah.
thought, look, the data says this must be the case, in my opinion, with high likelihood. But it's stupid, it's crazy, so some of the data must be wrong. My point was that some of the data has to be wrong because the data isn't consistent unless you have a universe with energy. And so I threw it out. People used to laugh and smile and all that. But yeah, I thought, this is too crazy to be true. But the universe is too crazy to be true sometimes.
So
And
that
and although I said the first time I really didn't believe it was when they discovered it. So that made me more skeptical. Anyway, yeah,
so uh that was between 1995 and 2012 when you published A Universe from Nothing.
yeah,
Um, there's so much advancement and that you were able to write a book. What's
yeah, yeah.
happened since?
Not a lot, to tell you the truth.
Yeah.
Because we know that there's dark matter in the universe. Dark energy appears to be there, but the questions are really hard. Dark matter we had hoped to discover. I spent much of my career proposing experiments and being part of experiments to look for dark matter, um, and unfortunately, it hasn't been discovered. But dark energy is much harder to. We can't do any laboratory experiments to detect it, so we have to think of astrophysical experiments, and they're really hard.
Yeah.
And moreover, dark matter, we have good theoretical expectations of what it might be, new types of elementary particles that we understand. But no one has an explanation of dark matter that makes sense. Dark energy, I mean, that makes sense. Except, the only people who like it are the people who write the papers, but no one else does. Um, and so it's the biggest mystery in physics, and I think it'll take a lot long. It's Here you have an idea that's very hard to test and very hard to get theoretical underpinning for. So it could, it's going to take quite a while before we get a handle on dark energy. I'm not sure we'll have a handle this century. So the questions have become harder. We have embarrassed ourselves by coming up with a standard model of cosmology, just like particle physicists embarrassed themselves in the 1970s by being so bright. They came up with a model of the fundamental interactions, the four fundamental interactions, three of them anyway: electromagnetism, the weak interaction, and the strong interaction. It's so good that they explain every experiment we've ever seen. And so there's not since 1975, more or less, with minor exceptions, there really hasn't been an experiment that's told us what new physics could explain why there are four forces or why the one force is so much stronger than the other. The standard model is embarrassingly good, and every time it looks like there's a crack in it, that crack goes away. Well, now we're in a similar situation in cosmology. This picture of a universe dominated by dark matter and dark energy, none of which we understand, appears to agree embarrassingly well with the observations. Now, there are tensions, and you'll read about them in the newspaper, Hubble tensions and other things, but those come and go, it's at the edge of measurement ability. There's always uncertainties, and I'm old enough to remember how dark matter had been ruled out 6 or 7 times before it was shown to not be ruled out. So we have this model that we're trying to find something. The model is a cosmological constant, and a constant energy of empty space 95% of the universe, basically. Well, no, sorry, that's 70% of the universe. 70% of the universe, energy of empty space. 25% or so of the universe, dark matter, some new type of elementary particle, and 1 to 5% of the universe being everything we see. And that's the universe that seems to explain what we see. And it's infuriating because we don't understand it. And we can't seem to learn anything about it.
Brother Krauss, you've given us so much to think about, and thank you for spending so much time with me. I want to ask one closing substantive question and then the question I teased at the very beginning.
Yeah.
So at the extremes of some of what you're talking about, you described a level of nothing that involves no laws, no physical laws. You've described particles that pop in and out of existence from nothing. At what point, and this might really be a linguistic question, at what point um, does the term supernatural apply?
Oh, I think supernatural implies that it can't be understood given the laws of physics. And
Yeah,
everything I've talked to you about is the reason I wrote the book, can be understood given the laws of physics or simple extrapolations of them. I
yeah.
thought you were going to ask another semantic question, which is what, and some people don't like this, but given these virtual particles and everything else, we see that really there's not much of a difference between nothing and something. Nothing and
Well,
something turn into each other all the
yeah.
time. And
Is
therefore,
is
the
nothing
vast,
something?
this dichotomy between those two things is just a different kind of something. The
Yeah.
absence. Yeah, yeah.
Well, I believe it or not, I'm not going to ask you about it, but I'm going to write off of that
Okay. Good.
and relate
Okay.
it to Bowie lyrics.
Okay.
But
Okay. Yeah.
you've been so great with giving me this time. So let me close as I told you I would. What is your favorite Bowie song?
Well, when you first asked me, I thought Starman because it sort of meshes with the theme that I knew you wanted to do. But then I've been thinking about it. And I've decided it's Heroes instead.
The song Heroes, the word nothing appears as often as the word heroes.
Oh, that's interesting. That's great. Well, you're an expert on that. You're an expert on that. I just like we can be heroes just for one day. We can be us just for one day. I like that.
Yeah. Um,
Um, wow. That's great. Well, if Bowie talked a lot about nothing, that's great. And all I can say is I'm glad he didn't copyright it, so I didn't have to pay his estate every time I wrote that number.
sadly, I can't play Heroes as an outro though for that exact reason.
Oh, okay. Yeah.
But
Okay. Great. Okay.
Professor Lawrence Krauss, thank you so much for joining me. This has been fascinating conversation, and I look forward to reading those books of yours that I haven't read yet, and whatever comes next. It's really gonna, I'm sure it's gonna be fascinating.
Well, thank you very much, and I appreciate it. It was a fun discussion. And when it comes to reading the books, as I say, what really matters is buying them. Okay, you take care.
Okay, thank you, Professor Krauss.
Okay, take care.
Goodbye.